Hi everyone, I'm Eli from UC Berkeley, and today I'll be talking about double regression with post-stratification, or as we call it, Dr. P. It's joint work with Avi Feller, also at UC Berkeley, and Aaron Hartman at UCLA. So the main problem that we're trying to address here is that even in moderate dimensions, survey adjustment via weighting is hard. And what I mean by hard is that there's a trade-off between sort of what we want to have and what we actually can achieve. So on one end is raking on marginals, where we reweight our responders to look like the target population based on the marginal distribution of our covariates. And on the other end, we have post-stratification, where we combine all of our covariates into small cells. So we interact everything, and then we make sure that those cell counts are the same across our sample and our population. Now, post-stratification is more desirable because under the typical missing at random assumption, it's actually going to get rid of non-response bias. Unfortunately, it's also less feasible. And that's because as we have more covariates and we start interacting them and creating more and more fine-grained cells, we actually very quickly are going to run into empty cells due to the curse of dimensionality. And as an example of this, in an example I'll talk about a little bit later, we have a pre-election survey before the 2016 US presidential election. If we can think about weighting on just education, which is the first thing on this x-axis, and we can look at the percentage of the population that's unrepresented if we weight on just education and just look at those cells. And there we actually have everyone because we have at least one responder for every education level. But once we add income and interact with region and race and sex and age and so on, we actually end up in a situation where we have so many empty cells that we're missing, more than half of our population. So post-stratification becomes totally unfeasible. So that's really the problem that we're trying to address here. We're trying to figure out how we can account for interactions in a principled way. And we know that interactions are really important, in particular to adjust for non-response. And in the example that I had talked about, we'll talk about more, we know that in the 2016 US presidential election, it was really important to weight on, for instance, education and race and region. So ideally, we'd post-stratify in these situations, but we can't, right? Because we don't have large enough samples to actually do that, and we end up with empty cells. So in this paper, we propose two things. First, we propose a calibration weighting estimator that approximately post-stratifies while at least raking on the margins. And what this allows us to do is to leverage the value of these interactions in a way that doesn't involve, ad hoc, cell concatenation and so on. And also, this optimization problem has a dual representation as actually fitting a multi-level model of non-response where we partially pool higher order interaction terms in this non-response model. Now, because we're only going to be approximately post-stratifying, our second contribution is to build on the doubly robust and bias correction literature to combine this weighting estimator with an outcome model to get what we call double regression with post-stratification, or Dr. P. So let's start by talking about how we're going to construct these weights that approximately post-stratify while at least raking. And to do that, I'm going to talk a little about notation. So we have n individuals in our population. We have an outcome y and a response r, and then we have d different categorical covariates. And we're going to collapse all this information down into a few sufficient statistics defined by the cells. So what we're going to do is we're going to interact all of our covariates and create j different cells where j, is exponential in the number of covariates. And then we're just going to count in the population how many units there are in that cell, and then we're going to count how many responders we have in that cell. So this is going to be in a vector with np and another vector nr. And the last bit of notation that we're going to use is we're going to have a binary vector that represents the kth order interaction terms for cell S. And what this means is best exemplified through a picture. So here I have a bunch of examples of these DSKs where the first column is D1, right? So this is first order interactions or margins, right? So if we look at the top row, the cell that we're looking at here is female and black. So in the margins, it's going to have a 1 for female and a 1 for black. And that's just denoted by these black squares on the white background. And then if we look at D2, which is the second order interactions, it's going to have only one square lit up and that's female and black, right? So here we just looked at the interaction between sex and race, but we can also include a bunch of other covariates, and then these matrices will become bigger. So given this setup, our goal is to impute the overall average for the population, which we can write, as just a weighted average of cell averages. And we're going to try to do this by taking a weighted average of the responders' outcomes, where we're going to weight the responses by these weights gamma hat. And we can also just sort of equivalently collapse all this down into weights by cells. So we're just going to re-weight the averages within each cell. And the key thing we're going to do here is we're going to assume that the outcomes are missing at random. So that means that within each cell, the average of the responders within that cell is equal to the actual population average in that cell, in expectation, right? So they're going to be unbiased. So given that setup, just to recap on raking and post-stratification, raking on the margins amounts to constraining the weights that we choose in some way, where in our notation, what we're doing is we're constraining the weights like this. So we're saying these D1s, which are just the first order margins, we're saying that the weighted sum of those D1s is equal to the sum of the D1s in the population, right? And that's just the raking written out as a constraint. Now, you can typically find weights that solve this constraint that are non-negative too, even if D is kind of moderate. But really, this only accounts for a linear approximation to the truth. Now, I put only in quotation marks because in practice, actually, the linear approximation to reality is fairly good, but we do know that interactions are particularly important often. So the other extreme here, again, is post-stratification, where we can actually just in closed form write out weights that'll exactly match within each cell, where again, the problem is we can't actually compute these because if a cell is empty, then this is undefined. But if it was feasible, it would be unbiased. So just sort of quickly, what do we actually want from these calibration weights? And in particular, is it worth it to try to post-stratify? And a way we can try to get at that is thinking about a population regression, where we take our whole population and we regress it on first order margins, second order interactions, third order interactions, et cetera. And then we can look at the estimation error for our weighting estimator. We find that it depends on two things. First, there's a bias term that comes from the fact that we haven't perfectly matched the interaction terms multiplied by their strength. And then there's a variance term that comes from the sum of the squared weights. So the takeaway here, and it's kind of hard to parse in real time, is that if the interactions are weak, it shouldn't be that big of a deal that we don't get exact balance on these higher order terms, right? So we do know that and think that main effects, right, this linear term is really important. So we can try to make sure that that's exactly balanced. And then second order interaction terms are also maybe important. So we should try to get as good as balance we can on that. But anything higher, we can actually maybe get away with only having approximate balance, only approximately post-stratifying. So the way that we're going to find weights here is basically just trying to minimize the MSE. So we're going to try to find these weights gamma, where for each order, or interactions of order 2 or higher, we're going to try to minimize the difference between the weighted sum of the respondents, so the amount of weighted responders that there are in this kth order interaction, the difference between that and the target. And the way we're kind of measuring distance here is via the L2 norm, or the sum of the squared weights, but you could also measure it differently if you wanted to. The second thing we're going to add is a penalty term. We're going to penalize the sum of the squared weights, which, because we're minimizing, amounts to trying to maximize effective sample size. And then the thing that we're going to add on top of this is a raking constraint. So we're going to constrain these weights to at least rake, which means that we're going to make sure that the margins between the weighted distribution of the responders and the target match exactly, and also that the weights are non-negative. So we have a hyperparameter here, lambda k, which allows us to move smoothly between these two extremes. On the one end, if we send it out to infinity, we recover raking because we put no weight at all on the approximate post-stratification portion, and we're just maximizing effective sample size subject to the raking constraint. And on the other end, if we send it to 0, then we're actually enforcing exact balance on all higher order interaction terms, which gives us post-stratification. In practice, we actually just kind of set this to 1, and what that does is implicitly, it just regularizes the cells by their size. So larger cells get regularized less, and smaller cells get regularized more. I don't have too much time to talk about this, but we can build off of new and exciting literature in the causal inference literature that connects these kinds of calibration estimators into propensity score weighting. This also has an older history where people understand this about raking. So essentially, solving this optimization problem through its Lagrangian dual also solves a different one where we fit a multi-level model for the inverse probability of response, where we have coefficients for first order terms and then also for higher order interaction terms. And we regularize those higher order coefficients, which actually gives us some insight into what's going on with post-stratification, where there's unregularized. We're trying to solve an unregularized optimization problem that might not be strictly convex. And once we add regularization, we can always find a solution. Okay, so in the time I have left, let me talk about double regression with post-stratification. And to do that, I'll start by talking about how we can use an outcome model here. So if we have an algorithm that computes predictions for each outcome, for each unit, we can aggregate these predictions into a cell level average prediction, which is mu hat S, and you can use your favorite predictive method here. And the way that we create an MRP style estimator is just by post-stratifying on these predictions rather than the outcomes. So our proposal to do double regression and post-stratification, or DRP, is to, instead of relying on the model everywhere, what we're going to do is we're just going to use it to fix where weighting is having problems. So what we'll do is we'll start with our weighting estimator, and then within each cell, we'll look at how different the weighted distribution is from the target distribution, and we'll adjust that by what the outcome model predicts the outcome should be in that cell. And this amounts to a bias correction. On the other end, we can start with our MRP estimate, and we can look within each cell at how different the MRP estimate is from the average from the responders and weight that accordingly to our weights. Now, building off of the doubly robust and bias corrected matching literatures, we can really view this in two different ways. In that first equation, what we're doing is we're using our weighting estimator and only using the outcome model to fix up cells where we're actually getting imbalance, where we're missing the mark. And the other equation, looking at that, we can see that what we're doing is we're starting with our MRP estimate, and then we're using weights to adjust for the fact that our MRP estimate might be systematically wrong in some cells that are underrepresented in our sample. And the weights tell us that. And lastly, you can see that if we actually post-stratify, then this whole thing collapses and the DRP estimate is just the weighting estimate. So the estimation error gets better. And now lastly, I'll just talk about an empirical example that I was discussing before, where we take a pre-election Pew poll and we try to impute Republican vote share within each state using the weighted CCS as ground truth. And again, here interaction should be important. First, just briefly, we can look to see whether this optimization procedure is actually doing what we expect it to. And we can measure that by looking at the percent imbalance difference. So just the difference in the reweighted population and the target population divided by the population size. So on the y-axis here, I have all the first order margins. On the x-axis, I have the absolute percent difference. What we can see is that multi-level weighting in green and raking in purple, which you can't actually see here, both get exact balance on the first order margins, as they are constrained to do. While post-stratification, where here we use an ad hoc cell collapsing procedure, has no guarantees on anything. If we look at second order interaction terms, again, post-stratification with these collapsed cells have no guarantees, and raking on the margins also has no guarantees. So you can see the purple dots start to move, but multi-level weighting actually, again, by minimizing these second order interaction differences, does better. And in third order actions, things get a bit more complicated. And lastly, let's look at this exercise from imputing state share. So what we do have here is on the y-axis, the MSE relative to unweighted, just the average of the Pew sample. And we'll look at raking on first order interactions and then approximately post-stratifying on second, third, fourth order interactions. What we see is that as we include more interactions, we are getting better MSE, right? Because here MSE actually matters quite a bit. We can now look at what happens if we combine with an outcome model. So the blue dashed line is just using a fourth order ridge regression. And here we see it actually does way worse than raking if you look at the first order interaction, but combining raking and that model actually improves over both, and our DRP estimator has better MSE. But then once we start balancing higher order interactions, the Dr. P estimate just kind of collapses to the weighting estimate because the outcome model is not picking up anything different. So to recap, what we do in this paper is we have a principled and parsimonious way to leverage the value of interactions by creating a middle ground between raking on margins and post-stratification. And because we're only approximately post-stratifying, we combine with an outcome model in this approach that we call Dr. P to adjust for the cells where weighting just isn't actually getting the balance that we expect it to. So I'm over time, but thanks so much for listening.